My name is Haleh. I'm a postdoc researcher at Dublin Institute for Advanced Studies. So I'm not part of a SPIN, so I really acknowledge that to have a time to give a presentation of my work, which is locating flowing conduits in Karst using passive seismic approach. And I really like to acknowledge my mentor and co-author, Crispin. So the idea of using passive seismic approach for locating flowing karst in conduits is that, as you see, near half of Ireland is underlain by limestone, which is depicted at different actually colors here due to different rocks. Yes, okay. So near half of Ireland is underlain by limestone, and it has been karstified in most regions, especially west of the country. And karst is a landscape that develops when the underlying rock is soluble, such as limestone and gypsum. And it's important to know where the flowing actually conduits are from different perspectives. For example, in terms of geotechnical and engineering applications, when building new roads and bridges, it's important not to interfere with those flowing conduits. And also in terms of groundwater flooding, that can be a kind of geohazards in Ireland. So the way that we looked at this problem is that instead of conventional structural imaging, we try to look at it as the source imaging, meaning that different physical processes in a water system, whether a surface water or subterranean water system in karst, such as turbulency of water flow, bed load transport, breaking waves, and any other physical phenomena, can induce tiny ground vibrations that can be detected by deploying seismic instruments near that water system, and then we can apply methods to figure out from which direction that signals are coming from. So we used a range of seismic equipments, including broadband seismometers, short period seismometers, and smart solenoids or geophones for our experiments. Oops. So before doing the experiment on karst, we started by doing an experience near a surface river, just to figure out how the signal looks like. So we deployed two arrays to locate the river-induced tremor. And also we left one of the stations near the river as a monitoring station for about 1.5 months to see if we can see any correlation between the seismic tremor and flow rate, as there was a permanent flow gauge in that river. So this is how the signal looks like after pre-processing. And this is the spectrogram of the monitoring station over a period of 1.5 months. And unfortunately, during our deployment, there was a construction site nearby, and as you see, the data is heavily contaminated by cultural noise, and sometimes it's hard to find that persistent signal between 11 to 14 hertz that belongs to the river and flow-induced seismic signal. So we extracted that signal in this frequency range over the monitoring interval, and we plotted it against the flow rate, and we see good correlation for most of the monitoring interval, except when there is actually intensive cultural noise. In the next step, we did the experiment on a simple karst site when the conduit is a simple source to sink a structure, shallow, within 5 meters subsurface. And here you see an example of the entrance to the cave. And the reason that we did the experiment here is basically it was shallow, simple, and also it has been dived, and we had access to the shapefile of this cave to ground truth our finding. So we deployed linear moving profiles of short period seismometers. So each line is 50 meters with 2 meter station spacing. And we had some linear profiles of geophones as well to record the cultural noise from the road nearby. So this is the total coverage of the study area over 5 days of experiment. So the white ones are the short period seismometers, the blue ones are the geophones, and this is how the deployment in the field looked like. So here in this slide, you see the data of the first linear profile consisting of 25 stations. We are interested in this persistent signal that changes from station to station and changes by time. And we assume that this is the subterranean flow-induced signal. So once we detected the signal, we need to locate it to make sure it's really coming from subsurface and it's really coming from karst. So we applied the amplitude location method, which is a well-established method in volcanoseismology to track and locate magma. And I think it's the first time we applied it in karst setting. So we applied this method for each individual linear profiles in different frequency bands that we saw that persistent signal. And then we plotted all the misfit maps in one plot. And interestingly, we see that, okay, there is one pathway along the dived conduit, and there is another one northeast of this area, which has not been discovered. Once we noticed that there is two sources of water in this area, we modified the amplitude location method to search for two sources at the same time. We noticed that, okay, there are really two water systems subsurface, and then this one has not been dived and discovered. And to make sure that the linear geometry that we had for the stations doesn't induce any bias in the location method, we tried to locate some of the hammer shots that we did for retrieving the velocity structure using this method to make sure that it's really working fine. Since we know where the hammer shot is, for example, here it's shown by the star, we applied the method, and then you see the misfits map, which is very close to the location, and also for the two-point source as well. In the next step, we did the experiment in a more complex conduit, which is like U-shape, and at some stage it goes to 60 meters subsurface. So this is the deployment we had, several linear profiles of geophones and short period seismometers, and two arrays. Again, amplitude location method could successfully locate the source of the flowing water here, which appeared as higher frequency in this site due to the change of a structure. And also, during the numerical simulation, we noticed that once we excite the conduit at one end, the wave field propagates through the conduit. For example, here we use the Ricker wavelet with peak frequency of 22 Hertz, and the power spectral density of the synthetic seismograms show double peak frequency, one near 20 Hertz, which is the peak frequency of the source, and one near 38 Hertz, which gives us this idea that probably the conduit is resonated with this approach. And we were wondering if we can see this in reality as well. So we did some ergon experiment near the resurgence point of the cave in the lake. And you see the ergon shots near the monitoring geophone station, which was deployed here. And we tried to track one of the shots here, for example, this one, last slide, using array processing. So you are seeing one of the shots here, below, less than 0.5 seconds. And we applied beamforming on a small windows on this signal using two arrays. And we could actually track the propagation of this wavefront along the conduit. And it's important as we couldn't apply the amplitude location methods at some parts of this conduit when it was deep. Okay, so in conclusion, we could quantify the seismic tremor in the river actually based on the seismic ground vibrations. And also we did seismic experiments on shallow and deep karst, and we could track and locate the flowing conduits there. And also we could successfully set the conduit under resonance and locate the conduit where it was deep, and we couldn't apply the location method in that area. And the next step would be using DAS and also applying the reverse time migration in these experiments. Okay, thank you very much for your attention.